Hello and welcome to my presentation on gas laws. So as a brief introduction, hello everyone, hello Mr. Bulusu, my AP chemistry teacher. This presentation was created as my final project for AP chemistry and I chose gas laws as that topic sparked my interest the most, even though it was relatively simple. Here we can see my friend on the left, Krish, provided me with this amazing picture of our classroom environment and Mr. Bulusu who teaches fabulously. And so here's a real life scenario. So I had a pack of Oreos in a sealed container, which had a lid at the top, and this is what it looked like on the ground when I was about to go on the plane. As we can see, it's flat. And after I was on the flight, as I went to go eat the Oreos, I noticed something strange, which had to do with gases. So the top was elevated. So how does this connect to gases? Well, firstly, we need to understand the science behind air pressure at different elevations. So the air column is a concept which is found using the idea that pressure is force over area, and since force equals mass times acceleration, by finding the mass of the air column and multiplying by the gravitational constant 9.8 newtons per kilogram, and dividing that by the area that the air column is on, we can find the pressure of that air column or the force over the area. So here's an air pressure versus altitude graph, and we can see that's an inverse relationship. On the ground, it's roughly around 101.3 kilopascals or 1 atm. And as we keep increasing the altitude, as we get to Mount Everest, it gets to around 33 kilopascals. So this is a free body diagram of the lid. And so as you can see, the force of the molecules inside are greater than the force of the molecules outside. And this is because the air pressure at the area that was packaged was greater than the elevation that I was at. As you know, the altitude, as you increase, the air pressure will decrease, which explains why the force of molecules inside are greater than outside, causing that inflated or ballooned effect. The reason
Hi.
why I chose the lid instead of the rest of the container is because the container has a more rigid material than the lid, which is plastic and thin. So you can see this effect better here. Alright, so moving on into Boyle's law. So the pressure of the molecules in a container are basically inversely proportional to the volume of the container, assuming that temperature is held constant. And this makes sense since if you had a fixed amount of molecules n in two separate containers and you had a smaller volume, the average distance needed to reach the container of the wall for the smaller volume would be a lot less, which would result in a higher frequency of collisions and a greater pressure than the container with the larger volume. And as you can see in the diagram, when you pull up, it increases the volume and decreases the pressure, whereas pushing it down decreases the volume and increases the pressure. Moving on, we have Charles's law, which says that the absolute value of a temperature is directly proportional to the volume. And this makes sense since a higher temperature means a greater kinetic energy, and that'll result in more frequent collisions, causing the volume to expand. But on the contrary, if the container is rigid, then an increase in temperature will cause an increase in pressure. And this makes sense since, as the ideal gas law, PV equals nRT, a temperature can cause a change in pressure or volume. And here we can see Charles's law, showing that when we increase the temperature, the volume also increases. Moving on, we have the hot air balloon concept of Charles's law. And so initially the volume is less because the gas particles aren't heated up, but as the gas particles are heated up, the gas inside the balloon becomes less dense, which allows it to float better, but also the balloon will expand. The balloon will then begin to rise, and going on to the idea of the buoyant force to expand upon this presentation, when the buoyant force is less than the gravitational force, it will fall, and when the buoyant force is equal to the gravitational force, it'll float, and if the buoyant force is greater than the gravitational force, it'll rise. The last law is Avogadro's law, and this law says that if temperature, pressure, and volume are equal between two balloons or containers, then the number of moles within it are equal, which also entails that a change in moles means either volume will change if pressure is constant, or pressure will change if volume is held constant. Okay, so last but not least, let's talk about the mathematics behind the air column. So if we have a 1 meter by 1 meter air column, and we know that pressure is force upon area, which is just mass times acceleration, which is gravity in this case, 9.81 over area. Then the mass of the air column times gravity, so the mass is 10,300 kilograms roughly, times 9.81 meters per second squared over the area, which is 1 meter squared, will give us our pressure, which is roughly 101.3 kilopascals. Now, if we have a plane, so I'm going to try to draw a plane, then that means that the actual mass of the air column, the mass of the air above it, is less, which is why the pressure is less at a higher altitude. Alright, so last but not least, we have the topic of mean free path, which is not discussed in AP Chem. This will expand upon my presentation. So, mean free path is the average distance traveled by a particle before undergoing a change in direction or energy, which is the result of a collision with another particle or the walls. To visualize this better, we can use a monatomic gas since it's spherical and not diatomic, it's one atom, such as argon or helium or even neon, to represent a situation where mean free path is easier to calculate. Since the shape of the atom is spherical, when the atom, let's call it A, undergoes movement, it'll sweep out a cylindrical shape which represents the volume in which collisions can occur between atom A and other particles. Alright, so here I have a diagram of a container with an atom A and B. And so of course when an atom A moves a distance, let's say lambda, it'll create this cylindrical shape, right? Which is shown in this blue right here. And that cylindrical shape represents areas where collisions can occur when this distance is traveled with other atoms that may be nearby, such as this one, or this one, or this one. However, for a collision to happen, it would only need to be on the edge of it, which is why we need to add the radius on top of itself. So this would be a radius plus another radius for that to occur, which is why when we say the equation, we say v equals pi d squared multiplied by the distance that it travels, d representing the diameter of the actual atom. And so when we do that, we get v equals pi d squared times lambda. However, the volume is just representing the cylindrical shape when there's a total container. So we need to use Boltzmann's ideal gas equation, which is much more useful as we can factor the total number of particles instead of using moles. And we get n over v equals p over kt. So this is a relationship that shows the amount of molecules per unit volume representative pressure over kt. And that'll help us basically generalize how many molecules will collide within that cylindrical shape. So we can do v equals pi d squared times lambda times n over v, and then we can just replace this with p over kt, k being the Boltzmann constant. So now, once we do that, all we need to do is set this equal to the number of collisions since we're factoring the actual volume. So this is number of collisions. And now we could set the number of collisions of 1 since since we're talking about mean free paths of 1 equals pi d squared times lambda times p over kt, and rearrange this equation to get lambda on that side. So we get lambda equals kt over pi d squared p. However, we also need to factor in this relative velocity concept, which is circled right here. The relative velocity between atom A and B is just VA minus VB, and when we square both sides, it's very useful because that'll help us get the equation for many other concepts, such as root mean squared velocity, as we see in the ideal gas chapter. So we get v squared equals v squared A minus 2 VA VB plus VB squared. And the dot product of VA and VB is just 0. So you can cancel that, and it turns out that VA equals VB as we can use the concept of ideal gases. And by doing that, we end up with our final equation where we get this and this. What this tells us is that we can multiply this by 1 over the square root of 2 to get our final equation for mean free path. So I hope you guys enjoyed this video. I hope this taught you a bunch of new things. Thank you for watching, and I'll see you later. Bye.